In this video, we're going to discuss the so-called gas laws. There are four variables that help us describe the properties of gases, and the first of these is the amount of substance in terms of moles, typically given the symbol of N in various equations. The second variable is the volume of the container that is holding the gas, which is typically given the symbol of capital V. The third is the pressure that the gas exerts, and this is typically given the symbol of P. And the fourth is the temperature, which is given the symbol of T. The temperature must be measured in degrees Kelvin rather than the degrees Celsius. Turns out that because we need to be in the Kelvin scale, we need to determine what the lowest possible temperature of a gas can be, and this is done by a plot of temperature versus volume for various gases. What you see here is that plot starting with initial volume of 4 liters for the elemental hydrogen. You see that the straight line becomes essentially an intercept on the x-axis where the volume of the gas is 0 at slightly less than 300 degrees, negative 300 degrees Celsius. Likewise, if we start with 2 liters, we end up extrapolating to essentially the same temperature with 0 volume. And if we do this for other gases such as helium, we get the same point. Liquid water, of course, the dashed line is because we have a phase change for water, so all we can do is measure values at high temperature and hope that the extrapolation comes back to the same value, and it does. And then finally, other gases such as N2O, laughing gas, again can be extrapolated back to essentially that same temperature. So, as a result, this lowest possible temperature on the Celsius scale is negative 273.15. We call that absolute zero on the Kelvin scale, and therefore all of our temperatures on the Kelvin scale are positive. And we must use these in our calculations using the gas law. It turns out that we know that there is a inverse relationship between the pressure and the volume, and this is known as Boyle's law. And so if we come up with our mathematical relationship of P times V, that must equal a constant. And so if we have a container where the volume can change, the pressure of the gas inside the container would equal the pressure on the outside. And so as a result, if we start with an initial volume of 1 liter and an initial pressure of 1 atmosphere, if we then were to take and increase the pressure on the outside of the container, then the pressure would be greater and on the outside than inside. This would cause the volume of the container in which the gases are located to get smaller, and at some point the pressure on the inside would equal the pressure on the outside, and this occurs when the new volume is half a liter, and therefore we would have had to double the pressure as a result of that to maintain our inverse relationship. So we can come up with a mathematical relationship for the initial situation and the final situation. So Pi times Vi equals Pf times Vf, assuming we have a constant number of moles and the temperature has not changed. We can understand Boyle's law, which is the relationship of pressure and volume based upon the kinetic molecular theory. And so it turns out that the pressure of a gas within a container is related to the number of collisions that occur with the inside surface of the container. So you see here the piston container where the volume is 1 liter with some number of gas molecules inside of the container. In this situation, the number of collisions with the piston is relatively small. However, if we were to then take and compress the volume of the container so that the volume becomes half as great as it originally was, now we have more collisions of the gas molecules with the piston portion of the container, and hence those collisions exert a greater pressure as a result of the frequency of the force acting on a certain area associated with that piston. And so hence the pressure doubles. So if we were to compress the volume even further, that would again double the number of collisions, and that would also then increase the total pressure inside of the container. And so our relationship of pressure and volume equaling a constant remains as we do this volume compression. The second relationship that we're going to discuss here is known as Charles's law, and when it is the relationship between volume and temperature, we know that there is a direct relationship between these two variables. So in other words, as one goes up, the other must go up, or as one goes down, the other must also go down. And so we can write this mathematical relationship as V divided by T is equal to a constant. And so if we use our piston and the gas contained within our container such that we have a constant pressure being exerted on the piston, or constant force per unit area, the gas molecules are randomly moving around within the container and causing collisions with the surface of the piston, counteracting that outside force. And so if we then add heat to the gases in the container, then we have a situation where we would have more collisions with the inside surface of the piston, and this would then cause the volume of the container to increase as long as we don't change the force that is being exerted on the outside of the piston. And so this is the situation of constant pressure, and as a result the volume temperature direct relationship must be maintained. Likewise, then we can write a new formula that describes the initial and final conditions, so that VI divided by TI is got to equal VF divided by TF, and this is something that is true when the number of moles of gas in the container and the pressure are held constant. Likewise, if we were to cool off the container, the volume should go right back to what the initial volume was, and so this is a completely reversible process. Of course, we can understand this based on the kinetic molecular theory in terms of the number of collisions of the gas molecules with the inside of the container. So again, molecules are in constant motion and colliding with the surface of the piston, and as a result we increase the temperature. That increases the average kinetic energy of the gas molecules, and of course they can, when collisions occur, they can transfer some of that kinetic energy to the piston itself, and so as a result then the piston rises to counteract the force that is being exerted on the outside, and so as a result then we have our direct relationship of pressure, of temperature and volume. Another relationship is the relationship between the number of moles of gas within a container and the volume of the container under constant pressure conditions. And this is known as Avogadro's law. So it turns out that if you increase the number of moles of the gas, the volume must increase. So that hence there is also a direct relationship between these two variables. And so we can then also derive the so-called molar gas volume, which is the volume that 1 mole of a gas would occupy under a set of standard pressure conditions. And turns out that the standard temperature and pressure conditions are known as 0 degrees Celsius, which is 273.15 Kelvin, and 1 atmosphere of pressure. So this is given the abbreviation of STP, and it turns out that any gas that behaves like an ideal gas will occupy 22.4 liters for 1 mole of that gas. We can combine all of the gas laws that we previously discussed into one equation so that we have the so-called combined gas law. As you see here, the pressure times the volume divided by the temperature for an initial and final situation. This can be a useful equation for solving various problems. So as an example, if we have a tire that contains 25.2 liters of air in the summer at a temperature of 37.8 degrees Celsius, which is quite warm, and the pressure is 2.33 atmospheres, if the season changes and the temperature drops to 0 degrees Celsius, the pressure in the tire will also drop to 2.10 atmospheres, and the question is, what is the volume of the tire? Assuming that the volume can readily change for the tire. If we then take our equation and rearrange it for the goal, which is the final volume, we have the equation as you see it here, and then we can plug in our variables. You'll notice that we have our pressure in atmospheres and volume in liters, but we have to also then take and convert the temperature in Celsius into degrees Kelvin by adding 273 to it. So this then gives us the temperature values of 273.15 for the final temperature and 310.95 for the initial temperature. You'll notice that the units of atmospheres cancel, and likewise the units of Kelvin cancel, and what you're left with is a unit of liters. And if we then plug all of our numbers into our calculator, we get 24.6 with 3 sig figs and a unit of liters. So indeed, the volume of the tire has decreased slightly as a result of the change in the season. This then brings us to probably the most useful of the gas laws, which is the ideal gas law. This is one that you should memorize. And so in this particular case, the equation is the pressure times the volume is equal to the number of moles times a constant, given the symbol of R, times the temperature in Kelvin. The R is known as the molar gas constant, and N, of course, is the number of moles of gas. So we can recognize that the units associated with the molar gas constant are often in liters, atmospheres per Kelvin, and mole. And this then gives a value for the gas constant of 0.082058. Likewise, there are other forms of the molar gas constant that have different units, and so we occasionally may use those values.